This is SpaceTime Series 20, Episode 54. Coming up on SpaceTime, new evidence shows brown dwarfs could be as common as stars, the closest look ever at Jupiter's Great Red Spot, and discovery of a new subatomic particle. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers believe our galaxy, the Milky Way, could contain over 100 billion brown dwarfs. The new findings, reported on the pre-press physics website archive.org, indicates that at least one brown dwarf is created for every 2 new stars that are born. Brown dwarfs are substellar objects which have failed to accumulate enough mass to sustain core nuclear hydrogen-protium fusion, the process which makes stars like our Sun shine. Instead, they fill the gap between the largest planets, which are about 13 times the mass of Jupiter, and the smaller stars, which are known as spectral type M red dwarfs. High-mass brown dwarfs can start out their lives as red dwarfs before burning off enough mass to cease protium-hydrogen fusion, although they often continue fusing deuterium and lithium. Since the discovery of the first brown dwarfs in 1995, astronomers have identified thousands more. The overwhelming majority of brown dwarfs detected so far were found within 1,500 light-years of the Sun, relatively nearby in astronomical terms. That's because brown dwarfs are intrinsically faint and therefore difficult to observe at greater distances. Most of the brown dwarfs which have been detected were all located in nearby star-forming regions, which are all fairly small and have a low density of stars. After first surveying 5 nearby star-forming regions, the study's authors turned their attention to the more distant star-forming cluster RCW38, located some 5,500 light-years away in the direction of the constellation Vela the Sail. This cluster has a high density of far more massive stars, many of which will undoubtedly go supernova. That makes it a very different kind of environment from other regions being studied for brown dwarf populations. Still, RCW38 is thought to be fairly typical of the type of environment where most stars in our galaxy are formed. The authors use the adaptive optics capabilities of the European Southern Observatory's VLT, or Very Large Telescope, in Chile. This allowed them to capture ultra-sharp images of stars in the RCW38 cluster. In fact, the quality of the observations allowed them to identify numerous relatively dim brown dwarfs, despite the overwhelming brightness of nearby stars in the cluster. The authors found approximately 1 brown dwarf for every 2 stars detected in the cluster. That's a similar ratio to what they had found previously in nearer, less dense star clusters. The fact that they found just as many brown dwarfs in RCW38 suggests that the environment in which the stars form, whether stars are more or less massive, densely packed or less crowded, has only a small effect on brown dwarf formation. One of the study's authors, Ray J. Award-Hanna from York University, says brown dwarfs appear to form in abundance in a variety of star clusters, making them ubiquitous denizens of our Milky Way galaxy. That's a view supported by co-author Alex Schultz from the University of St Andrews, who says because brown dwarfs form alongside normal stars in clusters, the work clearly suggests that there must be a huge number of brown dwarfs out there. In fact, the authors claim that their 100 billion brown dwarf estimation could be a significant underestimation, as there are many hard-to-detect lower mass and fainter brown dwarfs present everywhere in star clusters. In other words, it means brown dwarfs could be just as common as stars, if not more so. This is SpaceTime. I'm Stuart Gary. NASA's Juno mission, which has already revolutionised science's view of Jupiter, has just undertaken humanity's closest ever flyby of the gas giant's most enigmatic feature, the Great Red Spot. The Great Red Spot is a colossal high-pressure anticyclone, some 16,000 kilometres in diameter, which has been raging across the Jovian southern hemisphere for at least the last 350 years and possibly centuries longer. Jupiter is the solar system's largest planet. It's bigger than the combined mass of all the other planets and everything else in the solar system other than the Sun. The Juno mission is designed to study the planet's structure, its gravitational and magnetic fields, auroral activity, chemical composition, atmosphere, weather, and cloud patterns. The data should allow scientists to better understand Jupiter's origin and evolution, as well as its long theorized metallic hydrogen mantle. Juno's early science results are portraying Jupiter as a turbulent world with an intriguingly complex interior structure, enigmatic polar aurora, and massive Earth-sized polar cyclones. NASA's principal Juno investigator Scott Bolton from the Southwest Research Institute in San Antonio, Texas, says Jupiter's mysterious great red spot is probably the planet's best-known feature. He says now Juno and her cloud-penetrating science instruments will dive in to see how deep the roots of this storm go, and help scientists better understand how this giant cyclone works and what makes this storm so special. The data collection from the Great Red Spot is part of Juno's 6th science flyby over Jupiter's mysterious cloud tops. Perigove, the point in Juno's flight path where the orbit comes closest to Jupiter's centre, occurred on Monday, July the 10th at 18:55 US Pacific Daylight Time. That was 5 minutes to 2 on Tuesday morning, July 11th GMT, and 5 minutes to noon Tuesday morning Australian Eastern Standard Time. At the time of perigove, Juno was some 3,500 kilometres above the planet's swirling cloud tops. Just 11 minutes and 33 seconds later, Juno covered another 39,771 kilometres, placing it exactly 9,000 kilometres directly above the coiling crimson cloud tops of Jupiter's Great Red Spot. The first time in history we have been this close. All 8 of the spacecraft's scientific instruments, as well as the Juno imager, were armed and operating during the historic flyby. Juno's Great Red Spot encounter comes as the spacecraft celebrates the first anniversary of its arrival at Jupiter. Juno was launched on August 5, 2011 from the Cape Canaveral Air Force Base in Florida. The probe's now travelled more than 114.5 million kilometres since achieving orbit insertion around the giant planet. Each new orbit brings the spacecraft closer to the heart of Jupiter's radiation belt. But so far, the probe's weathered the storm of electrons surrounding Jupiter better than mission managers could have ever imagined. The spacecraft is undertaking a series of 37 extremely highly elliptical hyperbolic polar orbits, each with a period of about 53.5 days, designed to swing the probe deep down to within 3,400 kilometres of the swirling Jovian cloud tops, while avoiding the planet's crippling radiation belts for as long as possible. The CSIRO's Glenn Nagel from NASA's Deep Space Network Communications Complex in Canberra says the Jet Propulsion Laboratory's Goldstone tracking station in California had an unprecedented 4 antennas focused on Juno for the Great Red Spot flyby.
Yeah, so this is almost unprecedented. 4 dishes at the Californian station in our Deep Space Network actually receiving the data, 2 sort of acting as a backup slaves to the other 2 antennas. And then immediately after all that data has come down, our tracking station here in Canberra will be providing communication to Juno as it makes its next manoeuvre to do a course correction after it's done this very close encounter with the cloud tops of that giant planet.
Can Juno monitor the planet and send back data simultaneously, or do they wait till they're in a more opportune moment before they begin transmitting the data back to Earth?
Well, there will be actually data coming back, some radio science data in particular, because one of the really important things for people to remember about this mission is that this is really a chance for the scientists to look inside Jupiter for the very first time, really understand more of its structure. The pictures are kind of a bonus, and really a lot of the places that they're actually taking photos of have been actually voted upon by the public in the first place to say, what should we take a photograph on this flyby? And of course, a lot of people said, Great Red Spot, Great Red Spot.
And of course, it doesn't end there, does it? Because NASA have asked the public to help out with this one.
Yeah, I know in particular some of the people on the mission have been asked by the mission's principal investigator, Scott Bolton, to actually sort of say, okay, here's where the data is going to be. You voted on it as the public. We know there's some keen amateur image processors out there, and this is where the information will be. Whoever can get that data processed as an image to us first, and as long as it's a good version of that image, then that will become the official press release image with their name on it. So that's going to be quite an honour indeed. The amateurs out there do a great job. There's already been some brilliant animations and shots of the flybys of the planet looking at the North and South Pole and the cloud tops. Incredible views, and people are doing some really creative stuff with it, even scoring it to music as well. And this is a chance for them to take that enigmatic storm and really get this wonderful view and processing, not not just like taking a digital shot. This is having to process the red, green, blue filters, but not even that. Actually, they're looking in sort of the methane wavelengths, and the amateurs will have to actually take that and adapt it somehow to then make it into one of the filters to get sort of a roughly true colour image of the Great Red Spot. So it's going to be quite exciting to see what comes out from this.
And I think the amateurs will do a brilliant job because these people have equipment almost as good as the professionals and the skills to match as well.
Yeah, absolutely. And they're not only doing places like Jupiter, but Saturn, the wonderful images from the Mars rovers. But I think just recently, in particular, the stuff from the Juno mission, that was the goal of Juno's mission team, was to get the public more involved, to get school kids involved, to get amateur image processors involved, vote for the places where the scientists should aim the cameras at, take the photos, and then produce whatever they want from it, whether it's a fanciful artwork. I've even done some myself. And all of that gets put onto their mission website, and people can go and have a look at all this wonderful creative work being done just by regular people like you and I out there.
That's the CSIRO's Glenn Nagel from NASA's Deep Space Network Communications Complex in Canberra. Jupiter is the fifth planet from the Sun, with an average orbital distance of 778 million kilometres. A Jupiter year takes 11.86 Earth years. The planet has a diameter of 142,984 kilometres, yet it rotates extremely rapidly, with a Jovian day taking just 10 hours. Juno's encounter comes as astronomers continue to monitor the Great Red Spot in great detail. You see, recent observations from NASA's Hubble Space Telescope have shown that the Great Red Spot is shrinking and continuing to both change colour and shape. Back in the late 1800s, the Great Red Spot was estimated to be some 41,000 kilometres wide, some 3 times the diameter of the Earth. However, NASA's twin Voyager spacecraft measured the Great Red Spot at just 23,300 kilometres during their Jovian flybys back in 1979. That's still around twice Earth's diameter. But measurements taken by Hubble in 1995 saw the Great Red Spot shrink to just 21,000 kilometres. And by 2009, it was down to just 18,000 kilometres wide. Then observations in 2012 revealed a significant increase in the rate of shrinkage, which had now increased to a stunning 933 kilometres per Earth year. Just as dramatically, it was now also changing shape and colour, from the brilliant red oval we're so familiar with to a far paler orange circle. 2 years ago, on SpaceTime's predecessor Star Stuff, I reported that the Great Red Spot's diameter had dropped to just 16,500 kilometres. And as we mentioned earlier in today's show, NASA's data now shows it's down to just 16,000 kilometres. You're listening to SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Physicists have discovered a new subatomic particle. A report in the journal Physical Review Letters claims the newly found particle contains 2 charm quarks and 1 up quark. The doubly charmed, or if you prefer, doubly heavy quark baryon, was identified by scientists with the LHCb experiment on the world's largest particle smasher, the Large Hadron Collider at CERN, the European Organisation for Nuclear Research. Baryons are subatomic particles made up of 3 quarks, held together by the strong nuclear force which is mediated by the gluon. Quarks are elemental particles which come in 6 different types known as flavours. The flavours are called the up, the down, the charm, the strange, the top and the bottom, although the bottom quark is sometimes referred to as the beauty quark. The different flavours all have half-integer spin and differ only in their mass and charge. The 6 different flavours of quarks theoretically allow for many different potential combinations. However, all baryons observed prior to this discovery only contained 1 heavy quark. The newly identified particle has a mass of some 3,621 megaelectron-volts. That's almost 4 times heavier than the best-known baryon, the proton. Current theories always speculated that the particle must have existed. so it was always expected to eventually be found. But until now, physicists had been looking for baryons with two heavy quarks for many years without success. The new discovery will allow physicists to probe theories of quantum chromodynamics, the theory which describes the strong nuclear force. In contrast to other baryons in which the three quarks perform an elaborate dance around each other, a doubly heavy baryon is expected to involve the two heavy quarks orbiting each other, with the lighter quark orbiting the heavy pair. Measuring the properties of this double charm heavy will help establish how a system of two heavy quarks and a light quark really behaves. Important insights into particle physics and the Standard Model will be obtained by precisely measuring production and decay mechanisms and the lifetime of this new particle. The observations for this new heavy baryon were only made possible because of the high production rate of heavy quarks at the Large Hadron Collider during its 13 teravolt particle collision runs. Packets of subatomic particles such as protons are accelerated up to 99.999% the speed of light and fired in opposite directions around the collider, guided by cryogenically cooled electromagnets, to collide at one of 4 cathedral-sized particle detector experiments positioned around the 27-kilometre underground supercollider located below the Franco-Swiss border. The L8CB experiment, which is one of the 4 detectors, has unique capabilities allowing it to identify the particle collision decay products with high efficiency. I'm Stuart Gary. This is SpaceTime. SpaceX has set new standards for space launch capabilities with 4 separate Falcon 9 launches on 2 sides of the United States continent in under a month. The heavy launch schedule is part of a busy 2017 launch manifest for the Hawthorne, California-based company. The tight schedule began with the launch of the Dragon CRS-11 capsule from Pad 39A at the Kennedy Space Center at the Cape Canaveral Air Force Base in Florida back on June the 9th.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have liftoff of Falcon 9. Falcon 9 is cleared to tower.
For stage propulsion nominal. Stage 1 propellant utilization active. And back chill started. We have Nico 1.
Stage separation initiated.
Stage separation confirmed.
The Dragon was carrying supplies bound for the International Space Station. Now, as mentioned last weekend in SpaceTime's report on the Dragon's return to Earth, this was the first flight to reuse a Dragon capsule that had already flown on a previous mission. That was the CRS-4 mission back in 2014. Included in the payload for this flight were some 2,708 kilograms of experiments and equipment, including a swarm of astronaut fruit flies to examine how prolonged spaceflight affects heart function, and 40 astronaut mice for studies into treatments for bone loss in crew on long-duration spaceflights, as well as osteoporosis in patients on the ground. Other science experiments transported aboard the Dragon included 2 crystal growth studies, a payload to research the effects of microgravity on cardiac stem cells, new, more efficient solar panels, a new platform equipped with high-resolution digital cameras, as well as hyperspectral images and other equipment to study Earth from orbit, and the Neutron Star Interior Composition Explorer payload, which will be attached to the space station's exterior to study the physics of neutron stars. Following the launch, the Falcon 9 main stage successfully landed back at the Cape Canaveral ground pad for refurbishing for use on future missions.
MVAC condition confirmed.
Stage 1 boost back burn has started.
Stage 2 propulsion nominal.
Stage 1 boost back burn shut down.
Acquisition of signal Bermuda.
Stage 2 propulsion remains nominal.
Second stage continues to follow the nominal trajectory to orbit.
Acquisition in New Hampshire.
Stage 1 entry burn starting. Stage 1 entry burn shut down.
Stage 1 AFTSS saved.
Stage 1 is transonic. Stage 1 landing burn starting. Stage 1 landing legs deploying. Stage 1 engines have shut down. LZ-1, the Falcon has landed. Landing operators proceed with initial safing per procedure 11.100, section 3 on LZ-1 net.
Then, on June the 23rd, SpaceX launched the Bulgaria Sat-1, Bulgaria's first geostationary communications satellite. The flight, which also blasted off from the Kennedy Space Center, was only the second mission to use a previously flown and reconditioned Falcon 9 core stage. That rocket had previously been used for the launch of the Iridium-1 mission, which launched 10 Iridium spacecraft from the Vandenberg Air Force Base in January.
Falcon 9 is configured for flight.
10, 9, 8, 7, 6, 5, 4, 3,
2, 1.
RC copies.
GC, post-launch pad operations.
GC copies.
Falcon 9 is on its way to delivering Bulgaria Sat-1 to a geostationary transfer orbit. All 9 Merlin engines capable of putting out over 1.7 million pounds of thrust. We are coming up on max Q at 1 minute and 18 seconds roughly. We'll be passing through max Q, that is maximum aerodynamic pressure. Just crossed through it. That is one of the highest stressed states on the rocket. So we're over 20 kilometers above the surface of Earth. The engine plume expand at the base of the rocket.
Signal propulsion still nominal.
That is indicative that we are leaving Earth's atmosphere.
And vac chill has begun.
You just heard the call out that the Merlin vacuum engine on second stage has begun chilling in. This means that we are getting ready for 3 major events: main engine cutoff, MECO 1, stage separation, and second engine start. We'll talk about all 3 of them after they occur. In quick succession, MECO main engine cutoff, followed by stage separation, which was done by 4 pneumatic actuators on the forward end of our first stage, and then the glowing red nozzle of our second stage engine. We have a good ignition in space. We will have fairing separation in about 15 seconds. Just happened right now. It's like a good separation of the fairing. Bulgaria sat within the fairing of our second stage. This means we have left Earth's atmosphere. We used grid fins to guide the stage through the atmosphere to the drone ship. Now, those grid fins do look small, but they are about 5 feet long, about 4 feet wide. So they're rather large as we use them to guide ourselves back. Occasional puffs come out from the side of the stage. Those are cold nitrogen thrusters that we use to help orient the stage. Now, coming up in about a minute, we have our entry burn of the first stage. This is a 3-engine entry burn. For today's mission, since we are landing on the drone ship, we do not have a boost back burn. We only have an entry burn and a landing burn. 2 burns total for today's mission for the first stage. As I mentioned previously, our entry coming in for first stage is one of the highest heating and structural loads. So this is a very challenging first stage maneuver to land on our drone ship. Of course, I still love you.
Of course, I still love you has AOS.
You just heard confirmation that our drone ship has acquisition of signal, AOS, of the first stage as it's coming back.
First stage, stage 1 entry burn is starting.
This is ignition of the entry burn. This burn will last for about 20 seconds. 3-engine entry burn on the first stage.
Stage 1 entry burn shutdown.
We have a good shutdown, confirmation of a good shutdown of the first stage entry burn. Meanwhile, on our second stage, the engine burning, this burn will last about 8 minutes, 30 seconds. And then we will have a coast phase for the second stage before we do our final burn to put Bulgaria Sat into a geostationary transfer orbit.
Second stage, AFTS that stage.
And following stage separation for this mission, the Falcon 9 successfully landed back on SpaceX's East Coast drone ship, Of Course I Still Love You, which was positioned in the North Atlantic Ocean around 300 kilometres downrange from Cape Canaveral. Now, this means it was the first Falcon 9 to have landed on drone ships in 2 oceans, as its Pacific Ocean landing from Vandenberg was aboard SpaceX's West Coast drone ship. Just read the instructions.
We're coming up in about 30 seconds on our landing burn from the first stage, about 45 more seconds for this stage 2 burn.
Landing burn has started.
The confirmation of the landing burn has started.
Landing legs have deployed.
And it looks like we did have a good recovery of the first stage. Video feed did come back. That is touchdown for first stage on the drone ship. This was a 3-engine landing burn. Most challenging landing to date. Successfully touched back down on Of Course I Still Love You. Meanwhile, we have a good orbit for second stage. We are in a good parking orbit for second stage. We will be in coast phase till about the T++ 27-minute mark.
Built by Space Systems Laurel in Palo Alto, California, the 3,669-kilogram Bulgaria Sat-1 is based on an intermediate power variant of the SSL 1300 satellite bus. It has a 15-year design life and will provide direct-to-home television and data communication services across the Balkans and southeastern Europe. Just 2 days after the Bulgaria Sat-1 launch, on June 25th, SpaceX launched another Falcon 9 rocket, this time from Space Launch Complex 4E at the Vandenberg Air Force Base in California.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off the Falcon 9. Prop AVI RC and GMC proceed to computer 3.170 for post-launch flight operation. GC, move to post-launch pad operations to secure the pad on PadNet A.
Copy, Wilco.
Stage 1 PU's active.
F9 power until
T plus 53 seconds into flight. We've just heard the call-outs that engines are nominal. We've also got good status on the avionics system. We're coming up on maximum dynamic pressure. Merlin engines continue to perform nominally. We've heard a call-out of MVAC-D engine chill has begun. That indicates that propellants now are being fed to the front of the turbopump on the upper stage engine to chill it. As we get ready to light the upper stage engine, we're coming up on several major activities all at once. At about T plus 2 minutes and 24 seconds, we should have cutoff of the 9 first stage engines, stage separation, ignition of the upper stage engine, and right afterwards, reignition of 3 first stage engines for boost back burn.
Stage separation confirmed.
Coming up on T plus 3 minutes, stage separation, reignition successful. The first stage boost back burn is underway. We're coming up on fairing separation now around the 10 Iridium satellites.
Fairing separation confirmed.
3 minutes and 23 seconds into flight, you can hear the applause at SpaceX. Smaller crowd, many of our folks drove up actually to watch the launch from Vandenberg, just about 180 miles up the road from us.
The Falcon 9 used for this mission was the first fitted with new larger titanium grid fins designed to improve control for steering the booster, especially in strong winds, and to better cope with heating during re-entry. Previous Falcon 9s had all used aluminium grid fins. SpaceX says the new larger grid fins will also be better suited for the company's new larger Falcon 9 heavy launch vehicles, which are slated to begin flights later this year.
First stage, grid fins are deploying new dark gray titanium grid fins. They deploy a little more slowly than the old lighter weight aluminum fins. Second stage engine burn continues to look nominal. Chamber pressure is good. Trajectory looks good for the second stage. The grid fins are fully deployed. We're listening for when the drone ship has what they call AOS, acquisition of signal. That'll indicate the telemetry from the first stage is being received by the drone ship. The drone ship does not send commands to the first stage in flight. 4.5 minutes into flight, the upper stage engine continues to perform nominally.
Stage 1 and Stage 2 power and telemetry remain nominal.
Second stage continues to perform well, carrying 10 Iridium satellites to a parking orbit. The next major event is entry burn. We will light 3 Merlin 1D engines on the first stage. That'll slow us down for entry through the atmosphere. That's a fairly long burn. Entry burn is underway on the Falcon 9 first stage, bringing it back to the drone ship titled Just Read the Instructions, awaiting it in the Pacific Ocean.
Stage 1 AMTSS.
Entry burn is complete. The next burn will be the landing burn. So right now we're coming up on 7 minutes. It's actually 6 minutes and 40 seconds into flight. Stage 1 is headed back to the drone ship in the Pacific Ocean. Second stage continues to head south towards Antarctica as we head for a parking orbit, which is expected shortly after T plus 9 minutes. AOS on the drone ship means acquisition of signal. The drone ship now receiving telemetry from the Falcon 9 first stage. As a reminder, weather conditions are borderline out at the drone ship. Landing burn is underway.
The Falcon 9 successfully landed on SpaceX's Pacific Ocean drone ship. Just read the instructions.
Stage 2 power and telemetry remain nominal.
And you can tell by the cheering in the background. First stage, Falcon 9 Flight 38 has landed on Just Read the Instructions. Our drone ship in the Pacific Ocean landing at about T plus 7 minutes and 47 seconds.
The 10 Iridium telecommunications satellites were successfully deployed into low Earth orbit about an hour after the launch over a 15-minute window. Known as Iridium Next, to indicate they represent a second generation of Iridium satellites. Each of the 689-kilogram spacecraft use an Elite Bus 1000 satellite bus to provide voice and data coverage for satellite phones as part of Iridium's 66 satellite constellation. The first batch of Iridium Next generation satellites were launched back in January, and 6 more Iridium flights are still planned. Finally, on July 5th, SpaceX launched another Falcon 9 rocket, this one carrying the Intelsat 35E telecommunications satellite into geostationary orbit. The flight was again launched from Pad 39A at the Kennedy Space Center.
Falcon 9 is configured for flight.
T-minus 5, 4, 3, 2, 1. Ignition.
Stage of propulsion is nominal.
Vehicle is pitching downrange. Power telemetry nominal.
T plus 50 seconds into flight, you heard the call out on countdown net 1. Avionics is nominal. Earlier, we heard propulsion call out a nominal call for the 9 Merlin 1D engines. Next major activity coming up in just over 15 seconds. Maximum dynamic pressure. Falcon 9 currently has gone supersonic.
Vehicle is experiencing maximum dynamic pressure.
We've heard the call out. The vehicle has gone through the period of maximum dynamic pressure. That's where the velocity of the vehicle and the density of the lower altitude of the Earth's atmosphere combine to create the greatest loads on the Falcon 9. The Merlin engines throttled down and then throttled back up to full power in preparation going through this phase. So currently we're at full power, continuing to head towards stage separation, coming up at about T plus 2 minutes, 46 seconds. Now there'll be a sequence of activities that happen very rapidly. You'll hear MECO, main engine cutoff. The 9 Merlin first stage engines will shut down. 4 seconds later, we get stage separation. 7 seconds after that, the upper stage engine ignites to propel the second stage and Intelsat into the parking orbit. Let's watch and listen as we come up on MECO and stage separation.
Stage separation.
T plus 3 minutes, 5 seconds. You hear the applause in the background here in Hawthorne. A successful shutdown, stage separation, and ignition of the upper stage engine. The next major activity coming up is fairing separation.
Fairing separation confirmed. Second stage is following nominal trajectory.
Coming up on T plus 4 minutes into flight,
Bermuda,
we saw a successful separation of the payload fairing. Intelsat 35E attached to the top of the second stage, now exposed to the vacuum of outer space. We've also heard the call out that propulsion continues to be nominal. Trajectory looks good for the Falcon 9.
However, due to the mass of the satellite for this mission, the Falcon 9 core stage didn't attempt a re-landing. Consequently, it wasn't fitted with landing gear or grid fins. In fact, the 6,721 kilogram high-throughput Intelsat 35E satellite is the heaviest payload so far launched into geostationary transfer orbit by a Falcon 9.
Everything going well on the flight of Falcon 9 carrying Intelsat 35E. The second stage as it powers its way into orbit with shutdown of the upper stage engine. That'll be the first shutdown of the upper stage engine. There is a second burn planned later on as we pass over Africa. Everything continues to go well for Falcon 9 carrying Intelsat 35E.
Second stage continuing to follow nominal trajectory.
The second stage continuing to head east from Kennedy Space Center, going into the first of 2 planned orbits, in this case a low Earth parking orbit. Planned shutdown of the upper stage engine is coming up. This will be called SECO 1, second stage engine cutoff number 1. At the completion of the burn, we'll wait for the guidance, navigation, control engineering team to let us know how the orbit looks.
We have SECO.
And there you've heard it. We've had shutdown of the second stage engine right on time. Also looking at the trajectory data.
Good orbital insertion.
And there we hear also over countdown net, the GNC engineer confirms a good nominal insertion orbit. So this is the end of the first of 2 burns of the upper stage engine.
The rocket achieved a supersynchronous orbit, peaking at 43,000 kilometres. Built on the Boeing 702MP satellite platform, the Intelsat 35E is part of Intelsat's new EPIC fleet, equipped with C and Ku band transponders, providing broadband, video and mobile telecommunications services across Eastern North America, the Caribbean, South America, Europe and Northern Africa. The mission was the 38th Falcon 9 to launch, and the 4th launch in less than a month. The next SpaceX Falcon 9 flight is slated for August the 10th. It'll carry the Dragon CRS-12 capsule, transporting some 3,310 kilograms of supplies and equipment to the International Space Station. Included in the payload for CRS-12 will be the ISS CREAM, pronounced ice cream, cosmic ray detector. Ice cream is the next generation version of the CREAM high-altitude balloon experiments. by placing the science package on the space station at an average altitude of 410 kilometres means operating CREAM 10 times higher than it does on balloon flights. IceCream will be taking data almost non-stop during its 3-year mission. And because of its extreme altitude, there's no atmosphere for incident particles to scatter off before reaching the detector. Consequently, this experiment's expected to gather an order of magnitude more data than what the CREAM balloon experiments could achieve. I'm Stuart Gary. You're listening to SpaceTime. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.